So for those who like lists of instructions, here's how you go about predicting molecular geometries. You got to start with the Lewis structure. If you get the Lewis structure wrong, you're probably going to get the rest of it wrong. Determine the total number of electron groups. Figure out how many are bonding groups and lone pairs. And so this is fabulous. Why do they do this? Refer to table 10.1 to determine the electron geometry. You're not going to have table 10.1 on the exam. So I don't think that's a good strategy. And we're not going to do that. This is what I would recommend. Think about how balloons would arrange themselves. How would balloons get away from each other? And then imagine that the lone pairs are invisible balloons and draw a picture of what's left. Or use the names to describe what's left. Well, how do we draw these things? It's challenging to draw three-dimensional objects on a two-dimensional piece of paper. So we have some things that we do with wedges to help us represent three-dimensional things. So when we use just a regular straight line, we do that to represent a bond that is in the plane of the paper. So paper is two-dimensional, it forms a plane. If we hatch, they're eggs and they're hatching, but they're not hash browns. They're hatched wedges, okay? These little stripes on them. That is a bond that's going into the page. You can think of it as being under or behind the paper. So on the screen, the hatched wedge is behind the screen. The solid wedge is coming out towards you. So linear ones are easy to draw. Trigonal planar, bent, square planar, those are all easy to draw because they're two-dimensional. Tetrahedral, the way we typically draw this is we'll put two of the atoms bonded to the central atom in the plane of the paper, and then this one with the hatched wedge is going behind, and the one with the solid wedge is coming out in front. Here, the trigonal pyramid, we draw that just like the tetrahedral, but we just take that top guy off. Trigonal bipyramidal, so we're going to put the axial in the plane and one of the equatorial in the plane, and then one goes behind and one comes out in front. Now, could you draw it in a different orientation? Yeah, you certainly could. The way they're drawn here is to maximize the number of things that are in the plane and minimize the ones that are sticking out. It's just easier that way. So the seesaw, these three vertical ones here are in the plane, and then we've got an X going to the back and an X coming out to the front. Here's the octahedron. Here's like the little girl, and this is her tutu. These two are sticking out in front, and those two are behind. Square planar is easy. It's just all flat. Okay? So good news is on an exam, I'm giving you multiple choice exams, so you don't actually have to draw anything, but you need to be able to recognize what these symbols mean. Okay? So what if we have a molecule that's larger and has more than one central atom, more than one atom that's on the interior? Well, then things get a little more complicated. But what we do, like for this molecule here, is we're going to look at each of the interior atoms and figure out what the geometry is on those, and then we can kind of predict the overall shape. So here's the Lewis structure. So if we look at this nitrogen, it has 1, 2, 3, 4 groups. So what shape do the electrons make? A tetrahedral shape. We have one lone pair, so that converts it into what? A trigonal pyramid. Because we've got this hydrogen and the carbon, and then we've got the lone pair. So here's our trigonal pyramid There's the triangle part, and there's the pyramid part, the nitrogen. If we look at this carbon, how many electron groups does he have? 4. 4 groups, tetrahedral. Does it have any lone pairs? No. So the shape around this carbon is tetrahedral. This carbon, how many groups? 3. The double bond is 1 group. 3 groups form what shape? Trigonal planar. Any lone pairs? No. Then the shape, molecular shape, is the same as the electron geometry. So that one's trigonal planar. That one's flat in the plane of the screen. And this oxygen, how many groups? 4. 4 groups make a tetrahedral shape, but there's 2 lone pairs, so we get a bent structure. And so we can look at a large molecule and look at the individual pieces and see what kind of a shape they have. This is an important skill if you need to go on and take organic chemistry, because you need to be able to visualize and see what's going on with all these different shapes. The thing about the single bonds is they can rotate. And so you could draw it like this, but this hydrogen could also rotate up here, and it can spin around. Here, I'll show you on the model. So let's predict the geometry around each interior atom in acetic acid and make a sketch of the molecule. Well, here we have a structure, but it's not a Lewis structure. So we need to make a Lewis structure first so that we can see what we've got. So here we've got the carbon, and they are nice and tell us there's a double bond to the oxygen. And here's an oxygen, and it's got an H next to it. That means that that hydrogen is bonded to this oxygen. And then over here, we've got another carbon, and H3 tells us there are 3 hydrogens attached to that carbon. So we're going to spread it all out and show all of the bonds. And now we need to consider the valence electrons. So we should add them up. Come back. Thank you. We'll add them up. We've got 2 carbons. So 2, and each carbon has 4 valence electrons. We have 4 hydrogens. They each have 1 valence electron. And we've got 2 oxygens, and each oxygen has 6 valence electrons. So that's what, 8 and 4 is 12, and 12 is 24, right? Well, what we've got in here right now is 2, 4, 6, 8, 10, 12, 14, 16. 18, 20, 22, 24. I didn't want to put any lone pairs on this carbon because it already has an octet. But this was short and that one was short, and so by just giving lone pairs to the oxygens, I was able to come up with a good Lewis structure. Now that we have the Lewis structure, we can look at the geometries. What is the electron geometry around this carbon? Tetrahedral. What's the molecular geometry? It's the same because there's no lone pairs. So this one is tetrahedral. And what about the other carbon? That one will be trigonal planar. There are 3 groups and no lone pairs. So the electron geometry is trigonal planar and the molecular geometry is trigonal planar. How about this oxygen? The electron geometry is tetrahedral, but there's 2 lone pairs, and so the molecular geometry is bent. This oxygen is a terminal oxygen, meaning it's only bonded to one other thing. The interior ones are bonded to more than 1 atom. And so we're just worrying about these guys on the inside. So now we get to draw this. And this is where, you know, it kind of gets ugly sometimes. But we'll just give it our best shot. So I'm going to do carbon here, and to this oxygen, and to this hydrogen. I'm going to make those the three of the tetrahedron that are in the plane. And I'm going to have this hydrogen coming out, and this hydrogen going behind.
Isn't that a carbon?
It is a carbon, yes, thank you. Sorry. That's why people were looking at me funny. Yeah, you can't do that. You can't just change things. Okay, so there's the tetrahedral geometry around the carbon on the left. Then this guy here is a trigonal planar geometry, and that's easy because that's in the plane of the paper. So this is going to be a triangle. So I'm going to put the oxygen over here with the double bond and the other oxygen down here. So a trigonal planar 120-degree bond angles here. And then this guy is bent. And bent is also easy to do. We just don't make it a straight line.
Where would the lone pairs go?
Well, when we're sketching the molecule, we don't have to show lone pairs. The lone pairs are there. It's very important that they're there. Otherwise, the geometry would be very different, the shape of the molecule.
Would you put, like, both sets on one side of it? Yeah.
Well, for this oxygen, there are four sides, but they're none of them really next to each other. This is a tetrahedron. So no matter what two you have, they're next to each other.
No matter, sorry.
Okay, I'll show you. So that would be sketching it using using letters. If you want to make the atoms, you could draw circles for those. We tend to represent atoms as marbles or spheres, even though they really are not exactly like that at all. Any questions?